Okay, we're going to carry on with 3.5. So we're going to talk about stretching and shrinking the functions. So here I have the standard absolute value function. And let's look at what happens. So that function would look like this, right? So what we want to see is what happens if we do this. Sorry, no. First, this. Okay, so here's that function. And you notice that in the standard function, in the parent function we call it, we go over 1, we go to 1, we go up 1. Well, now we're just multiplying it by 2, so we go up 2. When we go over 2, instead of going up 2, we go up 4 because we're multiplying by 2. Okay, so what do you think will happen when we do 3 times? So now you see that instead of going over 1 up 1, we're going over 1 up 3. Instead of going over 2 up 2, we're going over 2 up 2 times 3, which is 6. So we're multiplying all of our y values by 3. So it makes it skinnier. Here we would have 4. And here we would have 5, I guess. So easy to see over 1 up 5, but over 2 goes up 10 because we're multiplying the answer, the y value. So what happens when we do a fraction? If I have 1/2 absolute value, and it only goes up half as fast, right? So I multiply all my answers. My 1 here is multiplied by 1/2. My 2 is multiplied by 1/2, so that makes it 1. If I do it by 1/4, we're just multiplying everything by 1/4, and so on. That would be 1/8. So the fraction makes it wider, right? And so this one was 5, right? It makes it, it looks like it's stretching it up, right? It's pulling it up. When we're coming down here with a fraction, it's almost like it's pushing it down, compressing it. So we can do this stretching for any of our library of functions, right? So let's see how it looks. What you need to know, though, is you need to know what the parent function looks like so that you'll know where to start. Right? So in this case, the dotted line is our parent function, x squared. And the solid line is 2 times x squared. Okay, so in the regular x squared, when I go over 1, I go up 1. So I multiply that by 2, and I go up 2. When I go over 2, I usually, in the parent function, I will go up 4. So I multiply that by 2, so now I'm going over 2 up 8. Okay? And the same thing on the negative side. Every y value then is multiplied by 2. So 1 goes to 2, 4 goes to 8. If we had 3, the normal one would be 9, so the new one would be 18. Here's one with the square root function, right? The dotted line is our parent function, right? The square root function. Over 1 up 1. Over 4 up 2, because the square root of 4 is 2, right? So this time I'm multiplying it by 1/2. This solid line is 1/2 x square root of x. So when I go over 1, instead of going up 1, I go up 1/2. Everything is half as big. It's really, I mean, when I look here, I can see on the graph it's half as big, but these aren't nice numbers to work with. But 4, square root of 4 is 2. That's our parent function, and half of that would be 1. And here's one with the absolute value. We already looked at it. This one is combined, though, with all the different things we've learned, the shifting and the stretching and the flipping. Okay, so here's our parent function. So here's the formula that we have. So first of all, we look at this negative. The negative means it's flipped upside down. Okay, so it's going to be going down, right? The 1/2 means it only goes down half as fast. This 1 inside here with the x means we shift it to the left 1. So I'm taking this x, I'm taking my vertex, I'm shifting it to the left 1, I'm shifting it down 3, and it's upside down. It's up, it's upside down and it's wider, right? Because when I go over 1, I don't go down a whole 1, I only go half down. So this is kind of how we can combine them. And you notice this format here, it always looks like A. This A tells us how much the stretch is or whether there's a flip, right? If A is negative, then we flip it. If A is positive, it stays in the same direction. And then we have, in this case, the absolute value, and we just typically refer to this as H and K for the two shifts. If the H inside here means X minus H means we shift it H, right? So in this case, H was -1. And then we have the shift on the Y out here. And this is kind of the standard form. This is what it would look like in absolute value. This is what it would look like for the squared function. You know, this is what it would look like for the cubed function. This is what it would look like for the square root function. Okay, so you have that idea that HK, that switches it to the new position. A tells us whether it's how much of a stretch and whether it's flipped. Okay, so there's one more kind of stretch or shrink, and that is horizontally. Okay, so that is when the stretching number is inside with the x. So, you know, if we had the absolute value of 2x, that is different than 2 times the absolute value of x. Okay? Or if we have 2x squared, that is different than 2 times x squared. Okay? So we want to look now at what happens when we put that stretch on the inside with the x. Okay, so here is, so the lighter one, it's not really dotted, but it is a smaller line, is my basic square function, right? The solid line, the darker line, is 2x squared. So it's like this one. Okay, so let's just take a look at this for a minute. You notice that if I had 2 times x squared, I'd go over 1 up 2, so that's not what we're doing. It does seem to go up 4, but it's not, well, in this case it kind of is. But here's what I want you to look at. I want you to look at what x is doing. Okay, so here is my x, and you see that my y value is 1. Well, if I go half that far, my y value is 1. And that's what's happening here. So, for example, look at 3. At 3, you see that my y value is 9. Well, half of 3 would be 1.5, and you see that my y value is 9. So you can kind of think of this as it's coming twice as fast, right? The x's are coming twice as fast, so it's kind of pushing them in. It's kind of pushed it towards 0. Okay? And the same goes on the other side. Let's look at one of our other functions. So here's the cubed root function. And the dotted one is the parent function, and the dark one is 4x cubed root of 4x. Okay, so here we have, when I do 1, my answer is 1, right? Well, my answer is 1 over here when I do 1/4. And maybe easier to see, if we go to 4, well, my answer's about right here, right? Yeah, let's put a little point on it and see if this will work. See if it'll stay right there. No, it stayed on the other line. Okay, so that was at 4. If I go to 2, no, if I go to 1, because I'm doing 1/4, right, then it's right at the same level as this one. Okay, so it's coming twice as fast. So what used to be at 4 now happens at 1. So it's kind of pushing it in towards 0. It's kind of compressing it in there, which is just the opposite of what it does the other way, right? If we have a 4, we would stretch it out. In this case, when it's on the x, instead of stretching it, it compresses it. So let's see what it does when we have a fraction there. Okay, so here's our absolute value one. Well, now, here my parent function is here, where we're at 2, right? So over 2, up 2. Well, when I put a 1/2 inside there with the x, that means that it's happening twice as far away, right? It's only happening half as fast. So what used to happen at 2 now happens at 4. So this horizontal stretch isn't quite as intuitive as the other. In fact, it kind of does just the opposite. And we're also used to looking at the y values, and in this case we have to kind of look at the x values. It's like the x's are happening twice as fast. Okay, so here's your quiz question for 3.5b. So looking at this graph, it's in the form, if you did the equation, it would be in the form a times x minus h squared plus k. So I want you to tell me what a is for this graph. Okay, so just write it as a single number. Don't forget to include whether it's positive or negative, but just a single number, and write that in the quiz on Canvas.